Okay, I'm going to go over the discriminant. The discriminant is the expression under the radical or the square root, which means the discriminant, when you hear the discriminant, it's talking about the expression underneath the square root. So that's our b squared minus 4 times a times c. So you can write the discriminant equals, it's your b squared minus 4 times a times c. There's a quadratic formula. That's a specific part of the quadratic formula, and it tells us some things about our solutions or our roots, okay? So the first thing we're going to look at is, what if the discriminant, b squared minus 4ac, is greater than 0, which means positive? What if it's positive, and it's a perfect square, which means you can take the square root of it. We'll just write perfect square. So what if it's positive and it's a perfect square? Okay. What we're going to look at is our notes from yesterday. When we look at our notes from yesterday, we see that on A and B, when we did the discriminant, the number underneath our square root, when we evaluated or calculated that in our or evaluated it, you got the square root of 100. Okay, that 100 is what was underneath the square root. It's a perfect square because we could take the square root of it. When we took the square root of it, we got a nice easy 10. Okay, again here, when we calculated the number underneath the square root, we got 361. The square root of 361 gave us a nice rational number, 19. Okay, so when you have the discriminant that's positive and it's a perfect square, you're going to have two solutions. 1, 2, we found two solutions, and they were, I'll say, nice, easy numbers. Okay, these were whole numbers. Okay, and this one you could write as a fraction. That means we are going to call those rational numbers because they can be written as a fraction. The interesting things about fractions are they'll either have a decimal place that will end, or they'll have a decimal place that goes on forever, but it's in a pattern of some sort. So here, when it's positive and it's a perfect square, the type and number of roots, you're going to have two roots, and they're going to be real numbers. Okay, there's not going to have any imaginary parts. So two real rational roots. Okay, you'll have two real rational roots. What that means is they're real, they don't have an imaginary part, they're rational because they can be written as a fraction, and they're usually pretty easy. So you can write that here on the type of roots. You can write two real rational roots for both of those. Okay, both of those discriminants were perfect squares and they're positive. Okay, we're going to look at what happens if this discriminant is greater than 0. So again, it's positive. But what if it's not? What if it's not a perfect square? Which means, what if you can't get rid of the square root? There's some kind of square root left. Okay. If we look at our examples from yesterday, we'll notice that E and F, example E and F, when we simplified the discriminant, we did 5 squared minus 4 times 3 times 1, we got 13. 13 is not a perfect square because you cannot take the square root of 13 and get a nice pretty number. You get an irrational number. We've been saying they're messy, okay? That means they go on forever without repeating. There's no pattern. That's what we call an irrational number, okay? So when you have a square root, when your discriminant is a number, but you can't make it pretty, you can't take the square root of it. Here, the square root of 28, we simplified it, but we were still left with a square root, okay? That's going to give us an irrational number, okay? You still have two solutions. We still had two answers, and I'll talk about that in a second. They're still real because they don't have an I in them. They don't have an imaginary part, but they're irrational because they have square roots left in them, which means their decimals go on forever without repeating. So two real irrational roots. So again, you can write that here and here. And why do you have two of them? Okay. Well, like we went over yesterday or earlier today, we got -5 plus or minus the square root of 13. You can break it apart to -5 plus the square root of 13 divided by 6, -5 minus 13 divided by 6. So it'll still give you two different numbers, but they're going to be irrational, and we can leave them like this if we want to. Okay. The next thing we're going to look at is what if the discriminant equals 0? If the discriminant equals 0, that's what examples C and D were from the previous lesson. Okay, when our discriminant, that what's under the square root, gave us 0, how many solutions did we have? We just had one. When the discriminant was 0, we just had one solution. Okay, is it real? Is it a real number or imaginary number? It's real because there's not an I in there. And then is it going to be rational or irrational? It's going to be rational because it can be written as a fraction. That's a technical definition. It's not irrational because we're not left with a square root that makes it quote, quote, messy. So here we have one real rational root. One real rational root. We only have one of them. We don't have two like we did down here. We have one. It's real. It doesn't have an imaginary part, and it's rational. So anytime you have a discriminant of 0, it's going to give you one real rational root. Okay. The last one we're going to look at is what if the discriminant is less than 0? What does it mean in like normal language that it's less than 0? Well, all the numbers less than 0 are negative. Okay. If the discriminant is negative, what kind of root, what type of root, what number of root? How many roots will we have? Well, here we'll look at G and H. Okay. When our discriminant, what was under the square root, when we simplified it, when it gave us a negative number, here we got -23, here we got -26, what was part of our answer? Okay, we had an I that was part of our answer. Since I is part of our answer, and we also have a real part, what do you call a number that has a real part and an imaginary part? We talked about that on Tuesday. We said those were complex numbers, okay? If you have 2 plus 3i and 2 minus 3i, you're going to have two complex numbers. Here, again, you have a real part that's 5, and then this imaginary part. If you have a real part and an imaginary part, that's going to be a complex root, okay? So we have two roots. One's adding, one's subtracting still. But they're complex. That's what happens when you have a negative discriminant. You'll have two complex roots. Now we don't say real because a complex number has an imaginary part. That's not a real number. Okay. The last thing we're going to look at is if we were to graph all of these equations, if we were to come back to these notes and graph them all, this is what you would see on your graph. On the graph here of your parabola, if there are two real rational roots or irrational roots, you're going to have a parabola that crosses the x-axis at 2 points. You're going to have two real solutions. You'll be able to see them on the graph. Sometimes they're nice, pretty numbers. Sometimes they're not. Okay. The next thing, if it's just one real rational root, that's when you'll have a graph and it'll just touch the x-axis at 1 point. Okay, that'll give you one solution. If it's two complex roots, because those have imaginary parts, your parabola will not touch the x-axis. So when we were graphing, we'd say that this would be no real solution. That's why it was important that we said real, because there is a solution. There's two solutions, but they have imaginary parts, so they're complex numbers. Okay, so that sums up the discriminant. Have fun.